we can look at I'm 2 on P versus P on 2, and that's pretty entertaining. So because like P on 2 is very boring because 0 is a square and 1's a square.
Yeah.
But 2 on P, there's something there, and it's not boring. And the fact that it's not boring, I think that really reveals that there can't be some kind of reciprocity law, because if 2 on P were related to the very boring P on 2, then 2 on P would be boring. But 2 on P is not boring. There's something to that. So you could start listing the primes where just start listing prime numbers for which 2 is a square. So like 7 is when P is 7. One, okay, I don't know if you want to buy. 17 is another one because 17 times 2 is 34, and 2 more than 34 is 36.
So hang on, before we go too fast, I don't think I'm going to be the only person who's going to struggle to visualize this. Would it be helpful if I made a grid that was the square numbers? So 1, 4, 9, 16, 25.
That's
and alongside that, the prime numbers, which are, I don't know if you're going to let me start with 2, 3.
Well, I don't know. You don't even need to do that. One way to sort of back solve this entire thing is to start. So one of your columns is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then your next column is the squares of those numbers. So 1, 4. Okay. Then the next column is 2 less than the square of those numbers. And then the final column is the prime factorization of those numbers. And the result is hilariously dramatic. I mean, it's just like, it's mind-blowing, honestly. I mean, because there's structure in what looks like a completely random list of numbers. And it's a sort of activity that you have people do, and it's like, why am I doing this? Like nothing good is going to happen.
So I teach a lot of year 7s maths as well, and what you've just described sounds like the kind of instructions I might give to them to keep them busy on a morning. But
torture your students.
But you're suggesting this someone should actually do this. So can I?
It's amazing. It's amazing.
So just for the listeners who, well, I'm not going to do it now because we'll run out of time.
It's so
but
good.
For the listeners who want to try this, you're suggesting we should start by writing natural numbers 1, 2, 3, 4, 5, etc.
Right.
And they do carry on. Then you said to do the
squares of those numbers. So just the squares of those numbers. Yeah.
I
so
can do
1,
that myself.
4,
1,
9,
16,
okay.
25, and
then
they also carry
two less than the squares of those numbers.
Take away 2. So negative
Yeah,
1,
take
2,
away 2.
7, 14.
Yeah.
Oh, sorry, take away 2.
Yeah, take away 2.
Oh, I was doing that. Yeah, on autopilot. 23,
Okay.
and they carry on.
And then the prime factorizations of those numbers that you get.
And I can't remember the notation for that.
I don't know.
So
Prime
factorization.
Yeah. I don't know. But so here it's not very exciting because a lot of those numbers are 14 at least is 2 times 7.
Yeah.
So then I mean what you end up getting is a whole lot of prime numbers that appear. And any prime number that appears in that list is a prime number for which 2 on P is 1. Because the value of n that you wrote on the other side is the thing that you square to get to mod that prime. So like if you take a look at the row that's 4, 16, 14, 2 times 7, if you work mod 7, that means that mod 7, n squared minus 2 is 0. That means that n squared is 2 mod 7. That means that n witnesses the fact that 2 is a square mod 7. So in this case, 4 squared is in fact 2 mod 7. So then what you end up doing is you got this giant list of prime numbers, and you keep turning the crank, and you keep getting more prime numbers out of this machine. And then at the end, you're like, well, what's common about all these prime numbers? Like how would you guess when a prime number appears on this list? And like, does 5 ever appear on this this list? Does 13 ever appear on this list? Does 37 ever appear on this list? Does 43 ever appear on this list? No. Like how do you know? How do you know which prime numbers do and do not appear as you turn the crank on this thing? And that's really the question of which primes have the property that 2 on P is 1, or the primes that don't appear are the primes for which 2 on P is minus 1. And the fact that half of them appear and half of them don't appear tells you that 2 on P is interesting. And that tells you that
Okay.
it's not going to be related to P on 2 because P on 2 is super boring. But there's definitely structure on, with 2 on P. So I
Um,
don't know. I worry about ruining the punchline. I'm told I can't ruin the
no, don't.
punchline of
No,
jokes, but
let's
I'll
leave
leave it
that. Let's
there.
leave that for the
Yeah,
viewer to finish for
yeah.
themselves and discover something exciting.
There's a pattern.
Um, what I'm worried about though is that we might not discuss the elephant in the room, and that is Cindy. Why have you brought this pretty trippy circle picture in?
The picture is a beautiful visualization of the p-adic integers, which is specifically two-adic integers. In general, a p-adic integer is a form of like the indefinite series. I can just give a definition like every number can be written as a0 plus a1 times p plus a2 times p squared times that is a set of p-adic integers, which is denoted by ZP. For example, like maybe we can kind of start off as like write 10 as two-adic. 10, which is 8 plus 2. So we're gonna have 0 plus 1 times 2 plus 0. Yeah, that's our first example as 10 as two-adic. And we sometimes write this as like the array format, which is 1, 0, 1, 0.
That's just
Yeah,
binary.
yes,
Okay.
yes, exactly. For two-adic, it is just like binary numbers. And also like the addition and subtraction and also multiplication, it works. Um, it's just really similar as all of the other like normal calculation. For example,
And I noticed the way you've written it down here, you've started by going in ascending orders of two, but then you've written binary in the way that we might expect a binary system, where this is counting the ones and this one is counting the twos and this one is counting the fours.
yeah, I just write it like the other way around. And also, for example, like the addition and subtraction is just a normal way as we're doing it, like learning this in primary school. Like for example, if we have 1, 0, 1, 0, and maybe I'll give it a number, another number like 1, 1, 1, 1. It's gonna give us 1, and then here 1 plus 1 is 2, but we're doing mod 2 here, so it's gonna be 0, and then we need to carry on. So 1, there's a carry on 1, and then we have a 0, and then we also need to carry on. So which is there, we're gonna get 3, and then there's a carry on 1. So right now, we're getting 1, 1, 0, 0, 1. Okay, so let's double check. Here 1, 1, 1, 1. We have 1 plus 1 to the power of 1 times, sorry, 1 times 2 plus 1 times 2 squared plus 1 times 2 thirds. So we have 1 plus 3, well, sorry. 1 plus 2 plus 4 plus 8 is gonna give us 12, 15. And then here we have 10. This one is 15. So it should give us 25. And but for this one, we're getting 1 plus 0 times 2 plus 0 times 2 squared plus 0 times 1 times 2 to the 3 plus 1 times 2 to the fourth, which is giving us 1 plus 8 plus 16, which is exactly 25. So we're kind of convinced that addition and multiplication is well, multiplication works really similarly, still in a usual way, but we do need to carry on. So that is kind of like a brief introduction about specifically two-adic, which namely is binary numbers. And also, here's another fact about p-adic number is for every integers, there is a unique representation of a p-adic number for one specific p. So also here in two-adic number, for every single integers, there's a unique representation for the unique two-adic representation.
So do you mean like -1 has a two-adic representation?
Oh, that's gonna. Oh, I actually really like -1. So for example, -1, we actually have another interesting fact. -1, we can write -1 as p minus 1 plus p minus 1 times p plus p minus 1 times p squared times all the way. And this one is actually infinite series. Well, infinite series. And why that works is just because like the middle term is going to cancel out. Sorry.
So I'm just writing down the two adics, but for -1, right? And then what happens if you were to add 1 to this value?
It's going to give us 0 and then carry on 1, 1, 1, 1, 1, 1.
So this term gives you 0, you carry the 1. This term gives you 0, you carry the 1. And does that ever stop?
Yeah, it's going to give us 0, 0, 0, 0, 0. For example, like the p-adic integers, for the positive integers, we can write it as a like binary form, like the normal way. And for negative integers, the reason that we can extend it into negative integers and also like fractions, is just because like maybe think about Laurent series, because we can extend the domain of p-adic integers into that to like the formal power series, like we can extend it into a to the power of -m p. Oh, that's kind of like in analogy of Laurent series. So we can extend, yeah, we can extend the domain and so that we can write, for example, -1, and we can also write, for example, 1 over 1 minus p. Here our p is 2, so we can, yeah, well, it's still -1. But for the other prime, 1 over 1 minus p, we can write it as also a infinite series, which is in fact 1 plus p squared plus all the way to p to the power of a minus 1.
Right. And I think that's why you were linking it back to the continued fraction as a sequence that we suggested might have a spooky relationship with negative values or maybe worse, irrational values or imaginary values. You've got a spooky relationship with these p-adic numbers that could also give you negatives and fractions despite being made up solely out of integers.
Yeah, thank you. Yeah.
Ah, brilliant. That's excellent. Thank you very much for sharing. Jim, I can see you've been busy and have put some things onto the onto your space. Can I move this over here so you can see it a bit
Yeah,
better?
yeah, you can move that over there. So I mean, I guess just trying to advertise, I can't help but advertise quadratic reciprocity, given that I'm
Ooh.
literally wearing the quadratic reciprocity shirt. But this is one of the problem sets that we give out at a summer math camp that I run for high schoolers in the U.S., the Ross Mathematics program, and the goal of that program is to get high schoolers to experience the awesome power of quadratic reciprocity. And one of the things that we do is hand out this table, and this table shows when something is or is not a quadratic residue modulo something else. And I think it's showing that with the vertical and horizontal lines. Just because I think when you look at it, you can kind of tell that something's happening. And I think when you look at it, it's actually not super obvious that there's a pattern there, so it's kind of surprising that there's any pattern at all, And anyway, I think that's really great. So
So if people who are watching this wanted to play with that on their own, would this PDF be available to them?
I can send it to you, and then you can send it to them. So,
Fantastic. I'll make
yeah,
that available to people
yeah. Anyway,
who
it's
also wish to descend into what looks like madness.
yeah.
Uh,
That's I mean, it's
so
just a classic thing. I don't know. Really
that's
love
great.
it.
So
Okay.
Jim, I'm fascinated by this diagram with the seven